Good afternoon, everyone. I hope you are all fine. I was in a hurry today to be able to record this session for you as fast as possible. I want to say that all the materials you will find on Moodle, of course, as you know, and all the previous lectures are already recorded and on the YouTube available for you. Also, I sent you today, just a few seconds ago, I sent you the PDF form of these slides, which is a detailed solution for the second midterm that covers starting from the definition of vector spaces, going to the basis, all the contents of the vector spaces, linear transformations, the eigenvalue and the eigenvectors, and also the part of the quadratic part. The one that I'm going to go through today with you is the main setting second midterm for 23-24 academic year. Also, I will choose a couple of problems from the previous year, which is, I believe, 22-23 academic year. So you will find both of them. Also, main resources are all fine. Will be found easily on the YouTube, and some of them, of these tests, actually the zip file of these tests was sent to you earlier on the group. So let's start together. Before solving or going through this session, I would deeply recommend that you will have to review all your course materials in order to take a very good advantage from this session. So all you have to do is to study all the previous materials, very good, and go through the main subjects, the what's a vector space, the definition of a vector space, what's a subvector space, how to issue such problems. We really solved a couple of problems on this, and also did go through the exercises for this part. How to get a basis for a vector space or subvector space, what are the conditions, what's the linear combination issue, how to solve it, it's a direct application on a solution of a system of equations, and so on. So I want to start with, as I told you, the shape of the exam. So this is the second test of linear algebras, January 15th, 24. You have 4 questions. This is 3 questions. That's the 4th one. The 3 questions starts from the definition of some proofs about a vector space, or what's a vector space, going through the intersection, the addition part. You will have also a very nice problem on a vector space of quadratic polynomials. I will go through it with you. Also, about the eigenvalue and the eigenvector evaluation. The last part, it's about diagonalization and will be the characteristic equation. We want you to prove something. The proofs depend mainly on the theories and limits that are involved in our course. And they are not just a few. You need to focus to try to solve as much problem as possible relative to your time, and of course use your pen. Every information or everything you write, it will count. So I need you to concentrate and step by step. Let's go for the first question, which states that let M2R be the vector space of a real 2 by 2 square matrices. For these questions, I would deeply recommend that you read it more than once. The first time, just read it to see which part this question is targeting. The second time, try to focus and memorize all the equations or all the laws that's relative to this part. So, once more, he's asking me that M2 be the vector space of real 2 by 2 square matrices. So, at the time being, I'm getting the matrices in front of my eyes. And he's talking about a vector space. Wait, it's a square matrix. It's a 2 by 2. what comes in your mind when you read this, just a part of a sentence, that the dimension is 4, because if you have a matrix 2 by 2, it can be break into the canonical form or the basis of the M2 by 2 matrices are 4. And I will show it to you just in the coming slide. He states that consider the subset W of M2R consists of all matrices A. Okay, very good. So we are talking about the vector space of a 2 by 2 matrices, and now he is introducing a subset. Look, a subset W of M2. Okay, what about this subset? What's the advantage or what the knowledge about this subset? This subset consists of all matrices A that are skew symmetric matrices. Of course, I know what's a skew symmetric matrix. The skew symmetric matrices are those class of matrices where you will find there is a simplest form for 2 by 2. Let's take an example. Let's say that 0, 0, A and negative A. That's a common example for skew symmetric matrix of 2 by 2. And of course, what's mark these matrices is that's A equal to negative A transpose. Okay, so this is a skew symmetric matrix, and this one of the characteristics of the skew symmetric matrices. By the idea, it's given to you. That's a skew symmetric matrix that's such that A equal to negative A transpose. So that's the definition of a skew symmetric matrix. So what do you need from me? Verify that W, this subset from the 2 by 2 matrices, is a one-dimensional subspace of M2. Record each thing that's required from you. He wants you to prove that or to show that this class of matrices, which is a skew symmetric matrix, is a part or a subset or a sub-vector space from the vector space of the square, all the square matrices 2 by 2. So this is very, very simple and easy to prove. So the first thing for a definition, if you remember, of a vector subspace, you will have to be sure that there is 3 conditions are satisfied with this skew matrices. These, number 1, the first of them, in order to have a sub-vector space, is that the 0 belongs to them. So the 0 element of these class of matrices belongs to them. Number 2, if you have 2 matrices and you get the addition of these 2 matrices, they will belong to W. And another thing, if you make a scalar multiplication, so just multiplying AV, it will also belongs to W. That's for A belongs to W, and for V, that's for V belongs to W, and A is a scalar quantity, so once you multiply them together. These are the 3 conditions. The number 1, the existence of the 0 belongs to the subvector space W, which is the subvector space of all symmetric matrices. Number 2, the addition of 2 skew symmetric matrices, it will develop a skew symmetric matrix. Multiplication by scalar in a skew symmetric matrix will also lead to a skew symmetric matrix. I want to start, for this one, it's trivial, it's known. If I have 0 belongs to this subvector space, yes, if A equal to 0, I will have a 0 belongs to the set of skew symmetric matrices. So what I want to prove now, if I have A and B belongs to W, and the K belongs to R, all of these conditions is satisfied with taking advantage of the criteria of the skew symmetric matrices. That's A equal to negative 18. So simply all I have to do, I will start from, if I have A plus B, okay, transpose with a negative sign, it's going to be equal to negative A transpose minus B transpose. And from the definition of the symmetry or the skew symmetric condition, I can replace negative A transpose by A or negative B transpose by B, which states that this proves the addition property for any two elements belongs to the subvector space of skew-symmetric matrices. Once you multiply a K by a skew-symmetric matrix, okay, so the result will be proving this criteria, which is the condition for a skew-symmetric matrix. So I will start exactly like this one from the part that states the negative of Ka transpose, which is simply K, the transpose of any number, it will be the same. So it's going to be a negative K times A2 transpose. And in the skew symmetry, negative A transpose equal to A, which means the second requirement, the third requirement in a subvector space is approved also for skew symmetric matrices. And this means that W is a subspace of M2 for any skew symmetric matrix. Okay, what I did at the time being is I'm checking that it is a subspace of M2. So the skew, now for the time being, we have proved that the skew symmetric matrices are a subset are a subspace from the vector space of the M2 by 2. If I want to prove or to verify that it's a one-dimensional subspace, I will start from the definition of the skew symmetric matrices, which is 0, A, negative A, and 0. This is the skew symmetric matrix for a 2 by 2, which simply can be done like this: A, 0, negative 1, 1, and 0. And once you reach this definition for a set of the skew symmetric matrices, such that A belongs to R. So this can be easily written as the basis of all skew matrices of a 2 by 2, which is 0, 1, negative 1, and 0, which makes this is the W subvector space that we are talking about. And there is just only one element that's the basis of this subvector space, which leaves us that the dimension of W contains just only one element. So it is 1, which means it's a one-dimensional subvector space. Now you have the proof or verification of this criteria. So once more, A is 0, A, negative A, and 0, which means if we take A as a common, we will come to 0, 1, negative 1, and 0. And this is the one-dimensional subspace of M2, which proves that this statement is completely verified. Before going to another thing, I want you to remember that if I have any 2 by 2 matrix, I've stated this and we need it shortly, but just in case I want to go through it with you. The general form of a 2 by 2 square matrix, it could be A, B, C, and D if you remember. And for this vector space of 2 by 2 matrices, it can be put on the following form, which can be put on A, 0, 0, and 0, plus a 0 and B, a 0 and 0, plus 0 C's double zeros, plus same way like 0, 0, 0, and D. And once you take A, B, C, D from all of them, you will get the basis for the 2 by 2 matrices, which could be on 1, 0, 0, 1. This is the canonical of this vector space of the 2 by 2 matrices, 0, 1, and 0, 0. And same way like it's gonna be a 0, 1, double zeros if you are following. And the last one, of course, yes, you are right, it's gonna be 0, 0, 0, and 1. If you remark that the dimension of the M2 by 2 is simply 4, because you have 4 elements forming the basis for all the 2 by 2 matrices. So this, how to go through the simple verification of W, which is the subvector space of all skew matrices. It's a one-dimensional subvector space. Here he's introducing that. Let V be a subspace of M2. So I have V, which is another subvector space from all the square matrices, such that V intersection W equals 0. So the intersection between subvector space V and subvector space W is 0. He already given to you this information. The V plus W equal to M2 by 2. So adding them together, both the subvector space V and the subvector W, it will develop M2. Determine the dimension of V. State for me the dimension of V. And this is really a very good question because it's targeting the part with the additional subvector spaces and the dimension. And we have a very good law I want you to remember. So I will start with the definition. Remark that to determine the dimension of V, we will need a connection to connect the dimension of V because I don't have enough information about V. The shape of the matrices or something. Just only it is related to W, that their intersection equal to 0, and their addition equal to the M2 by 2, or the set of, or the vector space of the square matrices. So I need a connection to connect them together. What's better than this law? The dimension of V plus W equal to the dimension of V plus the dimension of W minus the dimension of V intersection W. Once it came to your mind that I will need this law, then the continuation will be really very easy. So all I have to do is to make this substitution. Dimension V plus W, it belongs to the M2 by 2 matrices. This is the M2 by 2 matrices. And as you can see, the dimension is 4. So this is now known now. The dimension of W, which is the dimension of the symmetric matrices, just in the first part, I know that it's equal to 1. The dimension of V intersection W, which is 0, and it's given to me here. So all what's remaining is just to start substituting. I've stated that for you, that's dimension W1 from the first part of this problem. The dimension of V plus W belongs to the set of 2 by 2 matrices. Remember, the 2 by 2 matrices, so it's 4 dim. Dimension of V intersection W is given to you within this question is equal to 0. All I have to do is to just start substituting in this law. So instead of the addition is going to be 4. Dimension V is unknown, which will be easy for me now to get, which is dim V, just moving 1 to the other side. Dimension W is 1, and dimension V intersection W equal to 0. So all I have to do is to just verify that dimension of V equal to 3, which is beautiful, perfect. So from the first problem, if you remark, I have 2 things to prove. The first one, which is really simple, all you have to, as you said, as we saw, we have to prove that there is a 0, number 1, the addition really exists, scalar multiplication. The second part depends on the dimension law, which states that the addition equal dimension V plus dimension W minus dimension of the intersection. For question number 2, it's targeting also, as I believe, the part of the subvector spaces, and let's see. He's telling you let R2 of X be the space of polynomials of degree less or equal to 2. Now, I need you to remember 2 main problems. We already did go through them. Some of them are exponential functions, and the other were about quadratic polynomials or polynomials in general. Once you have a polynomial with a degree stated of n or m or whatever, the dimension relative to these polynomials will be n plus 1. So this is a second degree polynomial, so I'm expecting the dimension of the basis of this vector space, it's going to be 3. Remember this. So it's equal to the n plus 1. And he completes and states that with the usual sum and scalar multiplication. So it's already done. It's a subvector space or a vector space by itself. Show that, وريني, show me that B, which is 1, x and x squared plus 1, is a basis for R2. Clarify, you and justify, clearly justify your answer. All I have to do for the time being is just to try to prove that this is a basis for a polynomial of degree less than or equal to 2. So what does the basis do? The basis simply depend on how to find basis. We need to find or discuss two things. Number one, the independence, the linear independence of the set of vectors forming this basis. Number two, the spanning, that this set spans all the subvector space that you want to target. I'm going to say that once more. If I want to prove a certain set of vectors to be a basis for a specific subvector space, this is very, very simple. All I have to do is to prove that, number one, that they are linearly independent. I mean, for the these vector or set elements. Number two, I will need to show that they span all the elements of this subvector space. And this is very, very simple. So I need to do the linear independence, then check the spanning. How to check the linear independence? To check the linear independence, it's enough just to do this, to find a C1 times the first element or the first vector, which is 1, plus a C2 times the second vector, which is x, plus a C3 times x squared plus 1, and this result equal to 0. So as you can see, to check the linear independence, all we must do is to check. Check what? As I told you, this condition, that's C1 times 1, C2 times x, C3 x squared plus 1 equal to 0. And this is really very easy to prove, because all I have to do is to simplify this equation. So directly, it's going to be a C1 plus a C2 in x plus a C3 in x squared plus C3 equal to 0, which will lead to that you have C1 plus C3, which is a constant number, plus C2 of x plus C3 of x squared equal to 0, which leads to, in order to have a quadratic polynomial equal to 0, so the elements should all equal to 0. That's C3 should equal to 0, C2 should equal to 0. From these two conditions, I will have C1 plus C3 also equal to 0. That's C1 equal to 0. Which means the only way to have these elements, 1x and x squared, equal to 0 is just only by putting C1, C2, and C3 equal to 0. And that's the condition for linear independence. So all I had to do, as I told you, is to write that this is the general form of any vector which belongs to the quadratic polynomials, C1 times 1, C2 times x, C3 times x squared plus 1 equal to 0. And how to be sure that they are linearly independent? If just only the solution, that's C1, C2, and C3, or the coordinates of this combination equal to 0. And this is, as I told you, I will rearrange them in this manner. And equating a second degree equation with 0 will lead to that all these coordinates will equal to 0, which leads to that C2 equal to 0, C3 equal to 0, and so on. That's proving a linear independence. How to prove the spanning? So the first part was already very easy to prove. How to prove the spanning? That 1x and x squared plus 1 span all the set of quadratic polynomials. All the set of quadratic polynomials will be a number plus an x plus something in x plus something in x squared. So all I have to do is to check the basis. I'm talking about the dimension, as I told you previously. if you have a polynomial, so the dimension of the vector space of this type of polynomials equal n, which is the degree of the polynomial, plus 1. So this is a second degree polynomial, so its corresponding dimension is going to be 3. So now the basic dimension is 3. The given set will be, okay, remark, that's the given set which contains 3 elements or 3 components. That's any quadratic polynomial can be put on the form of 1x and x squared, so it's a 3 dimension, so it can span this set or this vector space of quadratic polynomials. This is as I told you, so which means that just multiplying c1 by 1, c2 by x, c3 by x squared plus 1, which is gonna be on this form, adding c3 and c1 can get any polynomial of a second degree, which means the spanning condition is already exists. So it is perfectly, now it is justified that you have proved the linear independence and the span. As I told you, the spanning is justified also. So you have a set now, which is 1x and the x squared plus 1, which proves, first of all, they are linearly independent. Number 2, they are spanning the vector space of the quadratic polynomials. So it is a basis, as I told you, for R2x. For number B, this is number A from the question. Number B, he's asking you about a linear transform, which transforms R2x into R2x. So I have a linear transform, or I have a transform, which will do, from the main domain, I have the set of quadratic polynomials. Once you apply the linear transform, it will be, the images will be on the defined form, which is x squared plus 1 b double dash minus 2x b dash. What's b dash or p double dash? It is the derivative of the polynomial you are moving. Okay. Or you are applying this transform on it. He said that, show that the matrix M, L, B, and B, so the matrix of the coordinate change of the basis from B to B, representing L in the basis B, considered in A, which is the B, of course, relative to the definition of 1x and x squared plus 1, and this is the matrix that we are talking about. We want to show him that it is okay, or it is correct statement. Actually, this is the matrix of the linear transform. So I will start from the main base, as I told you. The basis for the main domain, which is 1x and 1 plus x squared. Once you start putting your linear transform, you will go to the codomain, which applying the function, or which the images will be on the form of x squared plus 1 b double dash minus 2x b dash. Once more, I want to emphasize this, that my linear transformation, so now we are done with the first part, that's P, which is 1x and x squared plus 1, is already a successful basis for the R2 issue. Now I have a linear transform. Now I have a main domain, which contains some P of x. I will do a linear transform from R2 of x into another R2 of x. The shape of L is doing the following. L means that you will take 1 plus, let's write it this way, x squared, exactly like this one, x squared plus 1, b double dash plus, minus 2 of x, b dash. This is the image, this is the shape of the image, which will appear in the codomain. So mainly I'm taking the b of x, the b of x, L will do the following, will get the first derivative, second derivative, multiply them in this manner. I will have the images here. So this is the L of any b of x. It will be on this form. The matrix controlling this action it is proposed or need to be checked from you, it is that matrix. So how to go through all of this? I will start with the following. That's the matrix, which is 0, 0, 0, and so on. And in order to represent, which represents the linear transform, which from R2 into R2, as we stated previously, there is no new information here. In order to justify this, all I have to do is to prove that, or to be sure about that. If I have M times the coordinates of a B of X, it will equal to the L of B of X coordinates. So once you multiply these two matrices together, you will have the coordinates of the image on the other side. So bottom line, what I want to prove that, or want to show that this matrix works perfectly, I want to justify this statement. If I have an M and times B, it's going to be LB and B. So I will start with the following. Taking the basis, which is given 1x and x squared plus 1. And this is the codomain. This is the function that get the images of each element. I will start with each element in this basis and get its image, and then I will see that we can form the same matrix of transformation. So I will start with the basis representation. The basis representation, it's 1, x squared plus 1. It's exactly the same as I told you. So any p of x, any quadratic polynomial in the main domain can be written as C1 times 1, C2 times x, C3 times x squared plus 1. This is the basis of this vector space. And the coefficients or the coordinates are C1, C2, C3. I will need to get the coefficients relative to B, but for the after the transform. Okay, I will start with the elements. Let's start with the linear transform of 1, the linear transform of x, and the linear transform of x squared plus 1. Of course, L will do in 1 and in x and in x squared plus 1 this process. So in order to get the image of 1 or x squared plus 1, I will have to get the double derivative for each one of them. So if I started with number 1, for example, so if I have b equal to 1, L on 1, in order to get the image of 1, all I have to do, first, that's a b of x equal to 1, which leads to in the b dash equal to 0, and the b double dash equal to also 0. How to get the image? It's very, very simple. All I have to do is to make the direct substitution, so it's an x squared plus 1 times b double dash, which is 0, plus, minus 2x, minus 2 of x, times b dash, which is also 0. That's the image of 1 will be 0. So this leads that I have 0 equal to C1 plus C2 in x plus C3 in x squared plus 1, which leads to that in the C1, C2, and C3, all of them equal to zeros. So the first coordinate set, which is relative to 1, it's going to be the triple 0. This is exactly what we are going to see now. Okay, so for 1, the b dash, the derivative, is equal to 0. The b double dash for 1 is equal to 0 also. So once you take this information and start substituting in the L of x, so replacing b double dash by 0 and the b dash by 0, we will have that L1, the image of 1, will equal to 0. That's the coordinates are the triple 0. So this is the coordinates of the first part of this basis. I will redo all of this, but this time I will do it for an L of x. So I will start with L of x. Similarly like L of x, so I will need, in order to get its image, I will need to get, first of all, the first and second derivatives. So p equal to x, p dash will be 1, b double dash equal to 0. I will also take this information and I will start substituting here. So replacing b double dash by 0 and the b by 1. This is actually the result exactly as I told you. So here's x squared plus 1 times 0 minus 2x times 1, which will leave you with negative 2x. So now for the time being, once more, I will do it, let me do it here once more for you, or repeat these steps. Now I will get the movement of, or the image of f b of x equal x. So I have b of x equal x. In order to get L of b of x equal to x, I will need first to get b dash, okay, and to get b double dash. B dash, it's the derivative of x, which is 1. B double dash is the second derivative of x, or the first derivative of 1, which is going to be 0. Take these two information and start substituting in L, which states that 1 plus x squared times b double dash, so it's times 0, minus a 2 of x times b dash, which is 1, it's going to be negative 2x. Okay, to get negative 2x was relative to the basis beta, or b, which is given to us here. So negative 2x will equal to, supposed to equal to c1, okay, I'm sorry, c1, just only c1, then plus c2 of x, then plus c3 times x squared plus 1. As you can see, I'm talking about negative 2x only. So the only solution is that c1 should equal to 0, c3 should equal to 0, and the c2 should equal to negative 2. So that's the coordinates, which were c1, c2, and c3. Now start substituting. It's gonna be a 0, negative 2, and 0. So actually these are the coordinates relative to the movement of x. And this is completely stated here. This is b of x, b dash, b double dash. Just to start making the substitution, you will end up having negative 2x. So a negative 2x was relative to this basis. It's gonna lead to the following, that negative 2x equals 0, 1, negative 2 of x, 0 times x squared plus 1. So, which leaves us